Hello everyone, welcome back to another banger video. Today, we're going to be building an exciting project that involves detecting credit card fraud using machine learning. Credit card fraud is a significant concern in our digital world. Detecting fraudulent transactions is crucial to protect individuals and businesses from financial losses. In this project, we'll leverage machine learning techniques to identify fraudulent activities. Now before we get into the video, if you guys want to see more videos like this, drop a like down below. It helps us out tremendously with the YouTube algorithm. With that out of the way, let's hop right into it. Alright, so the first step is to understand our dataset. We'll load the dataset using the pandas library and take a quick look at its contents. So here we go ahead and import pandas. Let's go ahead and run that. And then a quick way to upload files on Google Colab is to just type in this code right here. You'll be prompted with this choose files button and then just upload the dataset. If you're on the desktop version of Jupyter Notebook, you just have to slide the or drag the dataset into your repository or your directory, and then you can use it right away. The dataset for this project will be in the description. It's on Kaggle. Just go to the description, download it, and upload it. All right, next we're going to go ahead and read our dataset. Right, so here we import the pandas library, which is commonly used for data manipulation and analysis. We load the dataset from a CSV file called creditcard.csv and use the read CSV function. The dataset is stored in a variable called data. By using the head function, we can display the first few rows of the dataset, providing us with an initial glimpse of the data structure. Now let's go ahead and gather some important information about the dataset. Alright, so the shape attribute of the pandas data frame returns the dimensions of the dataset, gives us how many rows and columns we have. By printing this shape, we get an idea of how large our dataset actually is. Additionally, the describe function provides summary statistics for each numerical column in the dataset, including the count, mean, standard deviation, and quartiles. This helps us understand the distribution and range of values in the dataset. Right? To tackle credit card fraud, we need to understand the distribution of fraudulent and valid transactions. Let's now separate them and calculate some useful metrics. Copy that. All right, let's make sure we didn't make any errors. Looks good. So in this code snippet, we create two subsets from the data set. Fraud, which contains the fraudulent transactions, and valid, which creates the valid transactions. We do this by applying a condition to the class column of the dataset. Transactions with a value of 1 in the class column are considered fraudulent, while those with a value of 0 are considered valid. The outlier fraction variable calculates the ratio of fraudulent cases to valid transactions by dividing the length of the fraud subset by the length of the valid subset. This metric helps us understand the imbalance between fraudulent and valid transactions. Next, we print the outlier fraction, which represents the proportion of fraud cases in the dataset. We also print the number of fraud cases and valid transactions using the len function and the condition on the class column. To gain further insights, let's examine the transaction amounts for the fraud and valid cases. In these code snippets, we display summary statistics for the transaction amounts in fraudulent and valid transactions separately. By using the describe method on the amount column of each subset, we obtain metrics such as count, mean, standard deviation, minimum, and maximum values. This helps us understand the range of distribution of transaction amounts in both categories. Understanding the relationship between different features in the dataset is crucial. Let's visualize the correlation matrix using a heat map. Alright, so here we import the Seaborn and Matplotlib libraries, which are commonly used for data visualization. We calculate the correlation matrix of the dataset using the core function on the data frame. The correlation matrix measures the relationships between pairs of variables in the dataset. Next, we create a figure and axis object using the plt.figure function and specify the size of the figure using fig size 12.9. Then we create a heat map visualization of the correlation matrix using SNS heat map. The Vmax parameter sets the maximum value of the color map, while the square parameter ensures that the heat map has square cells. Finally, we display the heat map using plt.show. So here's the heat map. It provides a visual representation of the correlation between different columns in the dataset. Darker colors indicate stronger positive or negative correlations, while the lighter colors indicate weaker or no correlation. Alright, so now that we've analyzed our data, it's time to prepare it for training our machine learning model. We'll split the dataset into input features and the target variable, and further divide it into training and testing sets. Alright, so in this section, we import the train test split function from the Sci-kit learn library. This function allows us to split the data into training and testing sets for our machine learning model. We assign the input features to the variable x by dropping the class column from the data frame using the drop class axis1 right over here. The target variable class is then just assigned to y. To process the data in the Sci-kit learn model, we convert x and y data frames into NumPy arrays using the dot values attribute. The process input features are stored in the x data variable, while the target variable values are stored in the y data variable. Finally, we use the train test split to split the data into training and testing sets. The x data and y data arrays are passed as inputs, and the test size parameter is set to 0.2 to allocate 20% of the data for testing. The random state parameter ensures the reproducibility by fixing the random seed to 42. Alright, so now it's time to actually build our machine learning model. We'll employ a random forest classifier, which is known for its effectiveness in classification tasks. Alright, so here we import the random forest classifier from the Sci-kit learn library, which represents the random forest model. We create an instance of the random forest classifier called RFC. Next, we train the model by calling the fit method on RFC and passing the training data xtrain and ytrain. The model learns from the input features and their corresponding values. Once the model is trained, we make predictions on the test set xtest using the predict method, and then we store the predicted values in the ypred variable. Alright, so this is going to take a while to train just because of how big our data set is. So we're just going to move on to trying, we're just going to write the code that's going to next assess the performance of our random forest classifier. We use various metrics like accuracy, precision, recall, F1, and the Matthews correlation coefficient. Now I'm just writing these out for now, but we're going to need the entire model to be trained before we can actually test how it did. Alright, so in this code snippet, we imported several metrics from functions from scikit learn, such as the accuracy score, precision score, recall score, F1 score, and Matthews correlation coefficient. Now, by comparing the predicted values with the actual values of the test set, we can calculate the accuracy, precision, recall, F1 score, and Matthews correlation coefficient. These metrics help us evaluate how well our model performs in detecting fraudulent transactions. And now I'll be back once this model is trained because it is going to take a while. Alright, so now that our model is trained, it took 6 minutes, we can go ahead and run this next code block to get our accuracy. And finally, what we're going to want to do is visualize the performance of our model. So we could see that the accuracy was pretty high, the F1 score and the recall were a little bit lower, but overall it seems to be pretty accurate in detecting fraud. So now let's go ahead and visualize the performance of our model using a confusion matrix. Let's make sure this is accurate. There we go. Right. So here we import the confusion matrix function from Sci-kit learn. This function allows us to compute a confusion matrix which displays the true positive, true negative, false positive, and false negative predictions made by our model. We create a list of labels to represent the classes, which are normal and fraud, and then we call confusion matrix to pass the true labels ytest and predicted label ypred as the inputs. The resulting confusion matrix is stored in the conf matrix variable. To visualize the confusion matrix, we create a figure using plt figure fig size 1212 to specify the size. Then we use sns.heatmap to create a heat map of the confusion matrix. The x-tick labels and the y-tick labels, anot, and fmt parameters are used to customize the heat map's appearance and annotations. Finally, we add a title to the heat map using the plt.title functions, set labels for the y and x axes using the plty label function and the pltx label function respectively, and we lastly display the plot using the plt show. Alright, so that concludes our coding tutorial. We've explored this code step by step and explained each line and its purpose. If you guys found this helpful, or if you guys want to see more, drop a like, subscribe, and we'll catch you in the next one. Hello everyone, welcome back to another banger video. Today, we're going to be building an exciting project that involves detecting spam messages using machine learning. In this project, we'll leverage machine learning techniques to identify spam messages and classify them accurately. By the end of this tutorial, you'll have a solid understanding of how to build a spam detection model using Python and Sci-kit learn. Now, before we get into the video, if you guys want to see more videos like this, drop a like down below. It helps us out tremendously with the YouTube algorithm, and with that out of the way, let's hop right into it. Now, before we dive into the code, let's make sure our environment is set up correctly. We'll need several libraries, including NumPy, Pandas, Matplotlib, Seaborn, TensorFlow, and Keras. If you haven't installed them already, go ahead and do that now. In this video, in this example, I'm going to be using Google Colab, so I won't have to install them, but if you're on the desktop version of Jupyter Notebook, you'll have to install them using pip if you're on Windows or whatever. Alright, so let's go ahead and import our libraries now. Wait, let's make sure that's good. Alright, and then next we're going to have to actually load our dataset or CSV file. So in Colab, an easy way to do that is just by typing out this code. This will prompt a small pop-up like this where you can go ahead and choose your file. Or I chose the wrong one. Alright, and then we can go ahead and read the data. Now, if you're in the desktop version of Jupyter Notebook, you can just you can insert the dataset by just dragging it into your project's repository. The CSV file and the dataset will be in the description. It's just on Kaggle. Yeah, you just have to go down there, download it. If you're on Colab, do what I just did. If you're on the desktop version of Jupyter Notebook, just slide it into your repository or into your directory. Alright, so now let's go ahead and read the data. So in this code snippet, we import the necessary libraries, including NumPy, Pandas, Matplotlib, Seaborn, TensorFlow, and Keras. We then read the dataset, which is stored in a CSV file called spam.csv. Next, we perform some data pre-processing steps. We drop unnecessary columns using the drop method, and then we rename columns to have more meaningful names, and additionally, we encode the labels as numerical values, mapping ham to 0 and spam to 1. Now let's move on to the next step. It's always a good idea to explore the data before building a machine learning model. This helps us understand the dataset and gain insights. Let's visualize the distribution of the labels in our dataset. Alright, so in this code snippet, we use the countPlot function from the Seaborn library to create a bar plot of the label distribution. And here it is. This allows us to see how many the number of ham and spam messages in our dataset. We display the plot using plt.show from matplotlib. So ham means that it's not a spam message, and spam means that it is a spam message. To train our machine learning models, we need to convert the text messages into numerical representations. Let's see how we can accomplish this. Alright, let's make sure we didn't make any errors. Looks good. So in this code snippet, we import the tf-idf vectorizer class from the sklearn feature extraction.txt to convert the text messages into tf-idf vectors. tf-idf stands for term frequency inverse document frequency, which is a commonly used technique for text feature extraction. We split the dataset into training and testing sets using the train test split from sklearn model selection. This ensures that our model is evaluated on unseen data. Now it's time to build our machine learning model. We'll be using the multinomial naive Bayes classifier, which is a popular choice for text classification tasks. Let's see how we can accomplish this. Alright, so in this code snippet, we import the multinomial NB class from sklearn naive Bayes. We then create an instance of multinomial naive Bayes model and train it using training data. Now we can go ahead and evaluate the performance of our model on testing data. The F1 score. Um, that's not supposed to be there. There we go. All right, so let's make sure we didn't make any errors. Yep, in this code snippet, we import several metric functions from sklearn metrics, including the accuracy score, precision score, recall score, and F1 score. We use these functions to calculate the accuracy, precision, recall, and F1 score of our model's predictions. So it's pretty accurate, it's pretty precise. The recall score is a little lower, the F1 score is a little lower, but it does seem to be pretty accurate. Alright, so that's going to be it for this video. We've successfully built a spam detection model using machine learning by leveraging the power of multinomial naive Bayes classifier and TF-IDF vectorization. We achieved accurate classification of spam messages. So I hope you guys found this informative and enjoyable. If you have any comments or suggestions, drop them in the comment section below. Don't forget to like, subscribe, and we'll catch you in the next one. Hello everyone, welcome back to another banger video. Today, we're going to be building a machine learning model that can detect fake news in Python. With the abundance of news articles circulating online, it's important to have the tools that can help us identify unreliable sources. Now, before we get to the video, if you guys want to see more videos like this, drop a like down below. It helps us out tremendously with the YouTube algorithm. With that out of the way, let's hop right into it. So as always, let's start by importing the necessary libraries and loading our dataset. For this project, we'll be using NumPy, Pandas, Sci-kit learn, and the passive-aggressive classifier algorithm. Right, let's make sure we didn't make any errors. Alright, while that's loading and downloading, let's go ahead and import our dataset now. Right, I think I misspelled linear. There we go. Alright, so an easy way to upload files on Google Colab is just by typing in this code right here. Then when we run this, we get a little pop-up where we can click choose files and select our dataset. If you're on the desktop version of Jupyter Notebook, you can just slide the dataset into your repository or your project's directory, and then you can just call it that way. The dataset for this project will be linked in the description. Just go down there, download it, and do whatever I just said. Alright, now let's go ahead and actually read our dataset. Right, and then I'll be back when the dataset is done uploading. Alright, now that our dataset is completely loaded, we can go ahead and run our read CSV function. So here we use the read CSV function from Pandas to read the dataset from a CSV file called news.csv, which is the one we uploaded here, and then we store it in a data frame called df. Alright, now let's explore the dataset a bit before diving into the machine learning part. Alright, so here we use the shape to get the number of rows and columns in the dataset, and we display it using df shape. We use head to display the first few rows of the dataset, giving us a glimpse of the data. Now, to prepare our data for training our model, we need to split it into training and testing sets. This will allow us to evaluate the performance of our model on unseen data. Alright, so here we extract the label column from the data frame using df label and store it in the variable labels. We use train test split, the train test split function, to split the dataset into training and testing sets. The text column represents the input data, xtrain and xtest, while the labels represents the target variable, ytrain and ytest. We specify a test size of 0.2 or 20% of the data and set a random state for reproducibility. Now we need to convert our textual data into numerical features. We use the TF-IDF, term frequency inverse document frequency technique for this. Now we're going to fit and transform the training set. Should we make any typos here? Looks good. Alright, so here we initialize a TF-IDF vectorizer object called TF-IDF vectorizer. This object will convert the text data into numerical features based on the TF-IDF algorithm. We specify English as the stop words, which are common words to be ignored, and set max df to 0.7, which ignores terms that have a document frequency of higher than 0.7. We use the fit transform function on the training set xtrain to fit the vectorizer and transform the text into numerical features. We then use the transform function on the testing set xtest to transform the text into numerical features based on the learned vocabulary from the training set. Now, with our data prepared, it's time to train our model using the passive-aggressive classifier algorithm. Alright, so here we initialize a passive-aggressive classifier. That object is named pack with a maximum of 50 iterations. We use the fit function to train the model on the training set, TF-IDF train and ytrain, and then we use the predict function to make predictions on the testing set, which is TF-IDF test, using the trained model. Alright, and lastly, let's evaluate the performance of our model by calculating its accuracy and creating a confusion matrix. Alright, so here we calculate the accuracy of the model by comparing the predicted labels ypred with the actual labels ytest using the accuracy score function. We use the print function to display the accuracy percentage, and then we create a confusion matrix using the confusion matrix function, which helps us visualize the performance of our model in terms of true positives, true negatives, false positives, and false negatives. Alright, and that's going to be it for this video. We've successfully built a fake news detection model using machine learning. Now, by leveraging the power of text vectorization and passive-aggressive classifier algorithm, we can identify potential misleading news articles. If you guys found this helpful or enjoyed the video, drop a like down below, drop a comment, subscribe for more, and we'll catch you in the next one. Hello everyone, welcome back to another video. Today, we're going to be building a machine learning model that can accurately classify breast tumors as benign or malignant. Now, before we get into the video, if you guys want to see more videos like this, drop a like down below. It helps us out tremendously with the YouTube algorithm. And with that out the way, let's hop right into it. Alright, so in this project, we'll be using the Breast Cancer Wisconsin Diagnostic Dataset, commonly referred to as WBCD. It's available in Sci-kit Learns Datasets module. Let's begin by importing the necessary libraries. Alright, so we import the NumPy module for numerical operations and the necessary components from scikit-learn. Specifically, we'll be using the load breast cancer function from datasets to load our breast cancer dataset. Additionally, we import train test split to split the data into training and testing sets, SVC or support vector classifier as our classification algorithm, and the accuracy score to evaluate our model's performance. Next, let's go ahead and load our breast cancer dataset. So we call the load breast cancer function to fetch the breast cancer dataset. The tumor features are stored in the data variable and the corresponding target labels, benign or malignant, are stored in the target variable. Next, let's split the data into training and testing sets. Alright, so using train test split, we split our data into training and testing sets. Here, we allocate 20% of the data for testing, while the remaining 80% is used for training. The random state parameter ensures the reproducibility of the split. Now, let's build our breast cancer classification model. For this project, we'll be using a support vector classifier. Alright, so here we initialize an SVC object as our model. SVM or support vector machines are powerful algorithms for binary classification tasks. We then train the model using the fit method, passing in the training features xtrain and the target labels ytrain. With our model trained, let's now make predictions on the test set and evaluate its performance. Alright, so here we use the train model to make predictions on the test set using the predict method. The predicted labels are stored in the predictions variable. To evaluate the performance of our model, we compare the predicted labels with the true labels from the test set and calculate the accuracy score using the accuracy score function. Right? And now we're gonna let's allow the user to input their own tumor features and see how the model predicts its class. Alright, so using the input function, we prompt the user to enter the values for the mean radius, mean texture, mean perimeter, mean area, and mean smoothness of any tumor. The input is stored in their respective variables as the floating point variables. Now let's create a NumPy array with the input features and reshape it to match the model's input shape. So here we create a NumPy array with the input features and reshape it to have a single sample with multiple features. This matches the shape expected by our model. Next, let's make a prediction using these input features. Here we use the predict method on our model, passing in the input features and store the predicted class in the predicted class variable. Now let's print the predicted class for the user's tumor. Right, and I guess we don't have it any inputs yet, so there's nothing to be declared, but the predicted class represents whether the model predicts the tumor as benign or malignant. Alright, so we have successfully built a breast cancer classification model using the Sci-kit library. We trained the model, evaluated its accuracy, and even allowed the user to input their own tumor features to see the model in action. So that's going to be it for this video. If you guys enjoyed, drop a like down below, drop a comment, and we'll catch you in the next one. Hello everyone, welcome back to another video. Today we're going to be building a machine learning model that can accurately recognize and classify handwritten digits. Now if you guys want to see more videos like this, drop a like down below. It helps us out tremendously with the YouTube algorithm, and with that out of the way, let's hop right into the video. Now in this project we'll be using the famous MNIST dataset, a collection of handwritten digits available in Sci-kit Learn's Datasets module. Let's begin by importing the necessary libraries. Alright, so first we import pandas for data manipulation, NumPy for numerical operations, and the necessary components from scikit learn. Specifically, we'll be using the load digits function from the datasets to load our handwritten digit dataset. Additionally, we import train test split to split the data into training and testing sets, k-neighbors classifier as our classification algorithm, and the accuracy score to evaluate our model's performance. Next, let's load the handwritten digit dataset into our program. Alright, so we run this. Alright, so we call the load digits function to fetch the handwritten digit dataset. The images of handwritten digits are represented as pixel values and stored in the data variable, and the corresponding target labels are stored in the target variable. Next, let's split the data into training and testing sets. Right, so using the train test split, we split our data into training and testing sets. Here, we allocate 20% of the data for testing, while the remaining 80% is used for training. The random state parameter ensures the reproducibility of our split. Now let's build our handwritten digit recognition model. For this project, we'll be using the k nearest neighbors or the KNN algorithm. We initialize a k-neighbors classifier object as our model. KNN is a popular algorithm for classification tasks. We then train the model using the fit method. We pass it through the training features xtrain and the target label ytrain. With our model trained, let's now make predictions on the test set and evaluate its performance. Alright, so we use let's make sure this runs. There's no predict. Oh, misspelled predict. There we go. So we use the trained model to make predictions on the test set using the predict method. The predicted labels are stored in the predictions variable, and then to evaluate the performance of our model, we compare the predicted labels with the true labels from the test set and calculate the accuracy score using the accuracy score function. Finally, let's print out the accuracy score to assess the performance of our handwritten digit recognition model. Right, so the higher accuracy score, or the accuracy score, represents the percentage of correctly recognized handwritten digits. So the higher the accuracy, the better our model is at classifying handwritten digits accurately. So we have a 98.6% accuracy score, which means that our model is very accurate um, at recognizing handwritten digits. Alright, so we have just successfully built a machine learning model that can recognize and classify handwritten digits using the Sci-kit Learn library. The accuracy score allows us to evaluate the model's performance, which proved that our model is very accurate. So that's going to be it for this video. If you guys enjoyed or found it helpful, drop a like down below, drop a comment in the comment section, and we'll catch you in the next one. Hello everyone, welcome back to another video. Today we're going to be building a machine learning model that can accurately classify images into different categories. Now before we get into the video, if you guys want to see more videos like this, drop a like down below. It helps us out tremendously with the YouTube algorithm, and with that out of the way, let's hop right into it. Alright, so in this project we're going to be using a popular image dataset available in Sci-kit Learn's Datasets module. Let's begin by importing the necessary libraries. Right, let's run this, make sure it works. So we first import pandas for data manipulation, NumPy for numerical operations, and the necessary components from Sci-kit Learn. Specifically, we'll be using the load digits function from datasets to load our image dataset. Additionally, we import train test split to split the data into training and testing sets, SVC as our classification algorithm, and the accuracy score to evaluate the model's performance. Now let's go ahead and load our image dataset. It should just be data. Score there. All right, looks good. So we call the load digits function to fetch the image dataset. The images are represented as pixel values and are stored in the data variable, and the corresponding target labels are stored in the target variable. Next, let's split the data into training and testing sets. Right, so using the train test split, we split our data into training and testing sets. Here we allocate 20% of the data for testing, while the remaining 80% is used for training. The random state parameter ensures the reproducibility of our split. Next, let's build the image classification model. For this project, we'll be using the support vector machines, or SVM. Alright, so we initialize an SVC object as our model. SVMs are powerful algorithms for building classification tasks or solving classification tasks. We then train the model using the fit method, passing in the training features xtrain and the target variable ytrain. With our model trained, let's now make predictions on the test set and evaluate its performance. Alright, so we use the train model to make predictions on the test set using the predict method. The predicted labels are stored in the predictions variable. To evaluate the performance of our model, we compare the predicted labels with the true labels from the test set and calculate the accuracy score using the accuracy score function. Finally, let's print the accuracy score out to assess the performance of our image classification model. Right, so this accuracy score represents the percentage of correctly classified images. The higher the accuracy, the better our model is at classifying images accurately. So our model is fairly accurate at 98.6% of the images were correctly identified. Alright, so we have just successfully built a machine learning model that can classify images into different categories using the Sci-kit Learn library. The accuracy score allows us to evaluate the model's performance. So that's going to be it for this video. If you guys enjoyed or found it helpful, drop a like down below, drop a comment in the comment section, and we'll catch you in the next one. Hello everyone, welcome back to another banger video. Today, we're going to be building an exciting project that involves predicting loan approvals using machine learning. Predicting loan approvals is a common task in the finance industry, and in this tutorial, we'll leverage machine learning to build a loan approval prediction model. By analyzing various factors such as income, credit history, and property location, we can make accurate predictions about whether a loan application will be approved or not. By the end of this video, you'll have a solid understanding on how to implement this solution using Python and Scikit-learn. Now before we get into the video, if you guys want to see more videos like this, drop a like down below. It helps us out tremendously with the YouTube algorithm, and with that out of the way, let's hop right into it. So before we begin, let's ensure that our environment is properly set up. We'll need several libraries including pandas, numpy, matplotlib, and seaborn. If you're on the desktop version of Jupyter Notebook, you can go ahead and install those now. If you're on Colab, let's just go ahead and import them. Right, the next thing we're going to want to do is load our dataset. So an easy way to do that on Google Colab is just to type in this code right here. This will prompt a little icon here where I can choose files. Go ahead and select our file. If you're on the desktop version of Jupyter Notebook, you just have to drag the dataset into your repository or into your directory, and then you can go ahead and call it from there. The dataset for this project will be linked in the description. Just go down there, download it, and then you can use it. And now let's go on to actually loading the dataset. Alright, so in these code snippets, we import the necessary libraries, pandas, numpy, matplotlib, and seaborn. We then use the pd.readCSV function to load the loan approval dataset from a CSV file called loanapprovalprediction.csv, which is the one linked down below, and then we assign it to the variable data. Finally, we use the head function to display the first 5 rows of the dataset, giving us a glimpse into the data structure. Now that we have loaded the dataset, it's time to pre-process it before training our machine learning model. Let's proceed with the code. Alright, so in this code snippet, we use the dtypes attribute of the data frame to check the data types of each column. We create a Boolean series object that identifies the columns with the data type object, which typically represents categorical variables. We then use the list object right here, .index, or this specifically in here, to get the column names of the categorical variables and calculate their total count. This information helps us understand the data's composition and identify which features require special treatment during pre-processing. Parentheses here. In this code snippet, we drop the loan ID column from the data frame as it's not relevant for our loan approval prediction task. We can use the drop function and specify the column name to be dropped along with the axis equals 1 parameter, which indicates that we want to drop a column. The in-place equals true parameter ensures that the changes are made directly to the data frame. Right, let's run that and move on. Alright, so in this code snippet, this allows us to visualize the categorical variables using bar plots. Let's go ahead and run it, make sure we didn't make any errors. So here we create a Boolean series, which is obj for object, to identify the columns with the data type object. We then create a list object calls for containing the column names of the categorical variables. Next, we create a figure with the 1836 with the size of 1836 using the PLT figure fig size 1836. We use a loop to iterate over each column in object calls. Inside the loop, we calculate the value counts of each category using column in the column using data called .value counts the function and assigning it to y. We then create a subplot using the plt.subplot function and specify the position of the subplot in the grid layout. And finally, we create a bar plot using sns.barplot with the x-axis values as the categories list y index right here, and the y-axis values as the frequency counts, or just y. The PLT xticks rotation equals 90 line ensures that the x-axis labels are rotated for better readability. To train our machine learning model, we need to encode the categorical variables into numeric form and analyze the correlation between the features. Let's go ahead and do that now. Alright, so here we import the pre-processing module from Sci-kit learn to perform label encoding on the categorical variables. We create a label encoder object and store it in the variable label encoder. We then create another Boolean series object to identify the columns with the data type object. Using a loop, we iterate over each column name in object.object.index, and for each column, we use the fit transform function method of the label encoder object to encode categories into numeric values. We update the data frame with the encoded values. Let's run this, make sure it works. So after encoding, we again check the number of categorical variables using the same approach as before. This ensures that all the categorical variables have been successfully transformed. Right. All right, so now we're going to go ahead and visualize the correlation matrix. Alright, so here we create a correlation matrix using the core function method on the data frame. This matrix measures the pairwise correlation between different features. We visualize the correlation matrix using a heat map, which provides a visual representation of the correlation values. We use plt.figure figsize 12.6 to set the size of the figure. Then we use sns.heatmap to create the heat map, specifying the color map, cmap, brbg, the format of the values, which is fmt equals 0.2 f for 2 decimal places, the width of the line separating the cells, so that was 2 here, and to whether to display the correlation values as annotations, which annot equals true does. Alright, now we have our data pre-processed. It's actually time to train and evaluate our machine learning model. Let's go ahead and do that now. Alright, so now we're going to split the data into training and testing sets. Or let's go ahead and run this, add it to a different block. 1. Make sure that's good. And now we're gonna go ahead and initialize the classifiers. Set the neighbors to 3 for the K and N. Alright, and now we're going to, and estimators. Oh, I forgot an S, should be N estimators. Alright, there we go. Alright, so now we're going to go ahead and actually train and evaluate our models. So first thing we're going to do is import an imputer to make sure that this works with random forest. Right. And then we're just going to go ahead and impute the missing values. Alright, go make sure we didn't make any errors. Looks good. And now we can go ahead and train and evaluate our model. Right, let's make sure it's good. Alright, so we do get pretty high accuracy scores. Now or this is for training, now let's go ahead and actually evaluate the models on the testing set. Alright, so in this code snippet, we import the necessary modules for model selection and evaluation from scikit-learn. We split the data into training and testing sets using the train test split function with the test size parameter to 0.4, which is 40% of the data for testing. We did 40% for this because the dataset was smaller than other datasets that we've worked with in the other machine learning videos. So we did 40% just to make sure that the testing set is different than the training set. We then train each model on the training set using the fit method, passing in the features xtrain imputed and the corresponding label is ytrain imputed, and we make predictions on the training set with the predict method and then store the results in ypred. We calculate and print the accuracy score of each model using metrics.accuracyscore function. Next, we repeat the same process for the testing set. We fit each model on the training set and predict the labels for the testing set, then calculate the accuracy score. This allows us to evaluate the model's performance on unseen data. Alright, and there we go. We successfully built a loan approval prediction model using machine learning techniques. We've covered data pre-processing, encoding categorical variables, analyzing correlations, and training multiple models for evaluation. Alright, if y'all found this video helpful, drop a like down below, drop a comment, subscribe for more, and we'll catch you in the next one.